Good morning, boys and girls. Welcome to the first amongst many lectures in this course. Now, what you're going to see when you look at this course is the chapters are broken up into 4 or 5 smaller lectures, small bites. Now, you also notice, hopefully, when you look at the home page, that we are skipping Chapter 1. Chapter 1, I really do not find it to be anything of importance. It's reviewing themes that you should have learned in high school biology. Now, for us to talk about living things, for us to talk about cells, for us to talk about enzymes, proteins, and whatnot, we have to start at the beginning. We have to start at the basic. So, as a repeat of what you've probably learned in Gen Chem 1, Gen Chem 2, we're going to start at the beginning. At the beginning, everything is composed of matter. Matter is of utmost importance. The importance of matter has to do with what is there and what isn't there. Matter is anything that takes up space, has some mass. Now, this mass may be something we can barely measure. It may be something that's theoretical, but it is there. We do recognize it. Now, when we start collecting like with like when it comes to matter, we find these things that we refer to as elements. I could take anything in this universe, start breaking it down. Take the chair or the bed you're lying on, start tearing it apart. Here's proteins, here's this, here's that. Proteins I can break down into amino acids. The amino acids I can break down into individual atoms. But the minute I break down those atoms, I get a mishmash of nothing. Unique, shaped the same. You try to break down elements, you get nothing. You get a mishmash. Nothing distinguishable. Now, hopefully you remember from your chemistry class that we designate everything with either a single or a double letter designation. When we're talking about the elements that we're going to find that are most probable or top. Now, it's not to say that you or your dog, your cat, your goldfish, whatever, plants, bacteria, are only made of these 4 things. No. You're going to find other things besides these 4. Silver, zinc, gold, sulfur. But those are in very small amounts compared to these top 4. Now, the elements, also referred to as atoms. Every atom has a specific shape, has a specific composition, a mixture of protons, neutrons, and electrons. These protons, neutrons, and electrons. A balanced atom has an equal number of protons and neutrons. Protons having a positive charge protons and electrons. Protons having a positive charge of 1, electrons negative 1. As long as they're in balance, the atom is uncharged. A balanced atom is a happy atom. Unbalanced atoms, well, they're highly reactive. Take sodium, Na+. What that means is it has one more proton than it does electrons, thus it has a positive charge. You look at chloride, Cl negative. Well, Cl negative means that it has one electron more than it has protons, thus it has a negative charge. Now we're simple things. Trying to think in three-dimensional subatomic space doesn't work for most of us. So what we have developed is this ability to draw out atoms in this configuration. Here's the nucleus with the protons and neutrons, and then circles around it, the orbits, where you will find the electrons. This is very simplified. Now, I'm not going to hold you to these. I'm just to the information on this slide. I just have it here so that we can talk about a few things. The atomic number and atomic mass. Okay, this is going to come into play here in biology in that having differences changes in the atomic number, the atomic mass, will change the overall shape of an atom. Change the shape, change its chemical properties, change its function. Atoms that have a different atomic number, atomic mass, we like to refer to these as things that have a different atomic number, atomic mass, we like to refer to these as isotopes. Isotopes for us are going to come into play when it comes to carbon dating, come into play when you look at periodic table. Top number is atomic number, bottom number is atomic mass. How many protons, total weight. Now, isotopes are going to be found throughout the natural world. These are not always man-made things. Sometimes they are, most of the times they are not. What we find is that things like here, they're showing isotopes of hydrogen. Under normal conditions, hydrogen is 1 proton, 1 electron. Sometimes things happen. You begin to collect neutrons. You get what's referred to as heavy hydrogen, giving you heavy water. The different shape of the atoms means that they have different chemical properties, different physical properties. One of the things you're going to hear me say throughout this semester, shape dictates function. Look at the shape of these 3 different hydrogens. They're not the same, thus they're not going to react the same. As you begin looking at the periodic table, there's a few things to keep in mind. Things that over here on the left are going to be more reactive than things over here on the right. Over here on the far right, you have the noble gases that, well, basically don't react with anything. Why? They're happy. They're in balance. Over here, not so much. Things are out of balance. Now, hopefully you learned in chemistry, there are multiple orbits. As you go up in orbits, the orbits get bigger, it can hold more electrons. We find at the left, the periodic table, that these hydrogen, lithium, sodium atoms, because of their shape, because they have this 1 electron hanging out there, it's highly reactive. Whereas over here on the far right, the noble gases, helium, neon, argon, well, look at that, they're pretty much full. They are happy. they are balanced. They're non-reactive. What we're going to find is most of the biologically significant atoms are going to be a mixture of highly reactive and those that are a little bit more stable but can still react, can still interact. This outer orbit, whether it's the first, the second, or the third, is referred to as the valence shell. First shell holds 2, second and third can hold up to 8 apiece. Why are these so reactive? Well, because they only have 1. As you get more electrons filling out the shell, you become more and more stable until it's completely full, like neon and helium, which are pretty much unreactive elements. So again, when you look at the periodic table over here, the far left, highly reactive, meaning they only have 1 or 2 electrons in their outer shell. Whereas over here, well, these aren't as reactive or totally unreactive as the noble gases because their valence shell is full. Now, as I said a few slides ago, we draw the circular orbit, the electron orbitals as circles because, well, humans were not that smart. It's hard for us to think in complex subatomic shapes. Because when it comes into the truth, well, this is what the orbitals look like. These orbits are actually more along the lines of predicted or probable places an electron will be found at any given instant. Snap your fingers. First orbits, or the third orbit, somewhere in here, an electron will be. Next instant, that electron's over here, somewhere in this probability cloud. So instead of being perfect circles, well, not so much. But how that affects us here in biology, well, I just want you to keep this in your back of your mind. Their atoms actually have a 3-dimensional shape. It is not Earth, Moon, circles. It's more of these probability shells, probability areas. Because the more of these probability areas for electrons to be gives a more and more distinct shape to that element. And the shape of an element, the shape of a molecule, the shape of an atom, the shape of a protein, the shape of a limb dictates function.